In the first lecture, we present the very basics of the thermodynamics, also the main definitions. What is a thermodynamic variable? What is a state? What is a transformation? What is a cycle? By means of those definitions, it is then possible to introduce the thermodynamic laws we will see in the coming presentations, as well as the relevant equations to use. The thermodynamic state is the condition of the system at a specific moment described by a set of measurable properties known as thermodynamic or state variables. If all the state variables are known, the thermodynamic state is completely defined. The thermodynamic variables can be either intensive, dependent upon system size, or extensive, independent upon system size. Some examples for intensive variables: the temperature, the pressure, the density or specific volume, the vapor quality, the specific enthalpy, the specific internal energy, and the specific entropy. For the extensive variables, the volume, the mass, the number of moles, the enthalpy, the internal energy, and the entropy. To define a state, it is sufficient to know the substance, which gas or mixture, two intensive variables, for instance pressure and temperature, and one extensive variable, for instance the mass or the number of moles. The thermodynamic variables can be represented in a thermodynamic diagram for easy use in the transformations. In the chart, only the intensive variables are plotted, so two of them are enough to define a state. The most used charts are temperature and specific entropy, specific enthalpy, specific entropy, pressure specific enthalpy, and pressure specific volume. In the example, we choose a medium, steam, and then the mass 1 kilogram, that is an extensive variable. We want to plot three different states, P1, P2, and P3. Also, we need two intensive variables for each state. We choose the temperature and the specific entropy. The remaining variables can be found. Here we represent only four variables to make it simple. By using the tool steam plot introduced in the starting presentation, we may represent the three states chosen. We do it using two different charts. The first one is the TS chart represented in this slide. The vertical axis is the temperature in Celsius, while the horizontal axis is the entropy in kilojoule per kilogram per Celsius. Within the chart are also represented in different colors the curves of constant transformations: constant pressure, constant density, constant enthalpy, and constant quality. We will speak about transformations later in this video. The orange bell, this one, represents the limit of the saturation region. By giving two input variables T and S, the tool calculates the remaining ones automatically. The second example is an HS chart. Here the vertical axis represents the enthalpy in kilojoule per kilogram, while the horizontal axis still represents the specific entropy as in the previous chart. In this case, the given inputs are the entropy and the enthalpy, and the tool calculates the remaining variables automatically. The third example is the pH diagram. Here the inputs are pressure in megapascal and specific enthalpy in kilojoule per kilogram in the horizontal axis. Here the limit of the saturation region is also represented by the orange bell. When the input parameters are given, that we repeat are specific enthalpy and pressure, the remaining variables are also calculated. If two independent variables are enough, they must be relationships among them. The relationships are the state equation, that can be different if perfect or real gas, for instance PV equals RT. Then we have the definition of enthalpy, H equals U plus PV, and other empiric formulas that practically link the entropy or the specific entropy and the internal energy with temperature and pressure. Some state variables are defined absolutely or relatively. In the last case, they require a reference state, like the entropy or specific entropy, the internal energy or its specific value, and the enthalpy or its specific value. The reference state P0 is arbitrarily chosen, for instance 0 degrees and 100 kilopascal. At P0 the variable's value is taken as 0. Notice that if we define the reference for entropy and the internal energy, then the enthalpy is generally different from 0, as we can see in this example. That because the enthalpy is the internal energy plus the pressure into the specific volume, and at the chosen reference conditions the pressure and the volume are not 0, since we remember they are absolutely defined. A transformation in thermodynamics is a fluid change from state A to state B along a path. It can be slow, quick, instantaneous, reversible or irreversible. During a transformation it will be produced work and or heat. This argument we will see in the next lesson. Most common transformations are keeping a variable constant. Isothermal, temperature is constant. Isobaric, pressure is constant. Isochoric, volume is constant. Isenthalpic, enthalpy or specific enthalpy is constant. Isentropic, entropy is constant. Isodynamic, internal energy is constant. There are also other significant transformations when a variable is not kept constant. For instance, the adiabatic, the heat transfer is 0, and the polytropic when pressure and specific volume are linked by the equation displayed. We see here some examples of simple transformations in the chart TS. We choose as gas air and the ideal gas model. The starting condition is 900 degrees Celsius and 4.7 kJ per kilogram per Celsius as entropy. The transformation PS-P1 is isentropic, since parallel to the vertical axis. The transformation PS-P2 is isochoric. The transformation PS-P3 is isobaric. The transformation PS-P4 is isothermal, since parallel to the horizontal axis. And because in a perfect gas, enthalpy and internal energy are only dependent upon temperature, the isothermal transformation is also isenthalpic and isodynamic. Some examples in the chart pH. The starting state is still the same as before, but in this case has different conditions, 1 and 1380 respectively in megapascal and kilojoule per kilogram. The transformation PS-P1 is isentropic. The transformation PS-P2 is isochoric. The transformation PS-P3 is isobaric, since parallel to the horizontal axis. The transformation PS-P4 is isenthalpic, since parallel to the vertical axis. The last transformation is also isothermal and isodynamic for same reasons said in the previous slide. A transformation can be reversible or not. Is reversible when it can be traveled in both directions. Irreversible when above is not possible. An irreversible transformation has also following properties. It is quick, it is out of equilibrium, there are heat losses, and if adiabatic, the entropy increases. An irreversible transformation is represented in a chart with a dashed line. In the picture is represented a thermodynamic cycle made of four transformations, two isothermal and two adiabatic. This is called Carnot cycle. We observe that the adiabatic transformations have entropy increase if irreversible. The blue cycle is reversible instead and can be operated in both directions, while the red dashed cycle is irreversible and can be operated only counterclockwise. A cycle is a transformation or a sequence of transformations that ends in the state as it is started. It generates or requires heat, it generates or requires work, and can be reversible or not, as we have seen in the previous slide. It is reversible if all transformations are reversible. And in this case, an opposite heat-work generation is expected when it is traveled in the opposite direction, for instance from clockwise to counterclockwise. In the picture is represented an organic Rankine cycle irreversible, generating work and requiring heat, and this can be traveled only clockwise. The picture is coming from the tool Fly Carpet. To clarify the meaning of work and heat and to learn how to calculate it, let's wait for the next presentation.